Welcome back. Tonight we're going to drift through the universe itself, not rushing through it, but letting it unfold around us, fact by fact, wonder by wonder. If you're enjoying these journeys into the cosmos, a like on this video helps others find their way here too, and if you'd like to subscribe, you'll have a new place to rest your mind whenever you need it. I'd also love to hear what you're curious about. Leave a comment telling me what topic you'd like us to explore together next time. Now let's begin. The universe has an age, a birthday if you will, though there is no cake, no celebration, no one there to mark the moment. It's approximately 13.8 billion years old. We know this not through guesswork or ancient texts, but through something more subtle, by measuring the cosmic microwave background radiation, or a kind of afterglow that still surrounds us. Imagine taking a photograph of a baby, then discovering that photograph is still somehow present in the room, faded but readable, floating in the air itself. That's what the cosmic microwave background is, the universe's own baby photos, still drifting through space, still available for us to study. The light has been travelling for so long, stretched and cooled by the expansion of space, but it's never disappeared. It's always been there, waiting patiently. A gentle reminder that even the cosmos had a beginning. Here's where things get strange in that quiet, wonderful way that physics sometimes does. The observable universe, the part we can actually see, is about 93 billion light-years in diameter, but the universe itself is only 13.8 billion years old. You might think that means we should only be able to see about 13.8 billion light-years in any direction. The math seems simple enough, except space doesn't play by those rules. Space itself has been expanding, and not just expanding, but expanding faster than light can travel through it. It's a bit like trying to walk across a room while the room itself stretches, the walls moving away from you faster than your legs can carry you forward. So the light from distant objects has been journeying toward us for billions of years, but during that journey space kept growing, kept stretching, carrying those objects farther and farther away. The result is this beautiful paradox, a universe younger than it is wide, if width even means anything on that scale. If you're lying somewhere right now, comfortable, maybe with the light falling gently on your pillow, you might feel like you're at the edge of things, or maybe in the middle. The universe, though, has no such boundaries. It has no center and no edge that we can observe. Every point in space, the spot where you are now, a distant star in another galaxy, a random point in the void between clusters, every single one of them can consider itself the center. It's remarkably democratic when you think about it. The cosmos doesn't favor any particular location. There's no special vantage point, no place from which everything else radiates. Wherever you are, the universe looks roughly the same in all directions. Galaxies recede from you at the same rate in every direction. It's a strange kind of fairness, perhaps, this refusal to privilege any observer over another. The universe doesn't care where you're standing when you look up at the stars. About 68% of the universe is made of something we call dark energy. That's more than 2/3 of everything that exists, and we don't really know what it is. We've named it. Dark energy sounds appropriately mysterious, appropriately vast, but the name is really just a placeholder, a way of pointing at something we've measured but don't yet understand. What we do know is that it's causing the universe to expand faster over time. Not just expanding, which would be strange enough, but accelerating. Imagine throwing a ball into the air, and instead of slowing down as it rises, It speeds up, defying everything you know about gravity and motion. That's what dark energy is doing to the fabric of space itself. We can see its effects, measure them with precision, watch galaxies accelerate away from each other. But the why, the what, the fundamental nature of this energy, that remains wrapped in quiet mystery. Then there's dark matter, which makes up about 27% of the universe. Add that to dark energy's 68%, and you're left with just 5% for everything else. All the stars, all the planets, all the gas and dust, everything you can see or touch or measure directly. Just 5%. We're essentially the universe's decorative frosting on a cake made of invisible ingredients. Dark matter doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any way we can detect. We know it's there because of gravity. It bends space-time, influences how galaxies rotate, holds clusters together in ways that visible matter alone couldn't manage. It's like deducing the presence of wind by watching leaves move, except the wind is invisible, odorless, and passes through everything without friction. Maybe you find that unsettling, or maybe there's something comforting in it. The idea that most of what exists remains quietly beyond our direct perception, content to work its effects without demanding acknowledgement. The cosmic microwave background radiation, that ancient light we mentioned, has a temperature, about 2.7 Kelvin, which translates to roughly minus 270 degrees Celsius. It's the coolest thing in nature, in a sense. The universe's own ambient temperature between the stars, in the vast stretches where nothing burns, nothing moves quickly enough to generate heat. This is the universe at rest, in a way. Not the violent heat of stars or the crushing pressure inside planets, but the baseline temperature that everything drifts toward when left alone for billions of years. It's a temperature that speaks of age, of things having settled, of energy having spread out so thoroughly that only this faint warmth remains. Perhaps there's something peaceful in that. The idea that even the cosmos has a resting state, a gentle background hum of ancient warmth still echoing from its beginning. The universe is remarkably flat. Not flat like a pancake, that's not quite the right image, but flat in a geometric sense. It means that parallel lines, if you could draw them across billions of light years, would never meet. They wouldn't converge like they might on the surface of a sphere, and they wouldn't diverge like they might on a saddle-shaped surface. They'd just continue, parallel, forever. Of all the possible shapes the universe could have taken, and there are many in the mathematics, it chose the simplest. Or perhaps chose is the wrong word. Perhaps the initial conditions just happen to fall exactly at the critical point where space neither curves inward on itself nor curves outward into infinity. It's a delicate balance, and the fact that we find ourselves in a universe with this particular geometry is either a cosmic coincidence or a clue to something deeper. Maybe you can decide which feels more right as you drift off tonight. There are an estimated 2 trillion galaxies in the observable universe. 2 trillion. That's about 285 galaxies for every person currently alive on Earth. If you wanted to assign each human their own collection of galaxies, you could give them hundreds each, and still have plenty left over. Each of those galaxies contains somewhere between 10 million and a trillion stars depending on size and type. Each star might have planets, moons, asteroid belts. The numbers become almost meaningless at that scale. Too large to visualize, too vast to hold in your mind all at once. But maybe that's okay. Maybe you don't need to grasp it all at once. Maybe it's enough to know that the universe is generous with its stars, extravagant with its galaxies, content to scatter them across distances so large that most will never be visited, never even be observed in detail. There's something almost wasteful about it, and something beautiful. The first atoms formed about 380,000 years after the Big Bang. Before that moment, the universe was too hot for atoms to exist. Electrons couldn't stick to nuclei. They'd zip around. Just too energetic to be captured, like trying to catch a hummingbird with your bare hands while standing in a hurricane. But as the universe expanded, it cooled. Gradually, gently, the temperature dropped to a point where electrons could finally settle into orbit around atomic nuclei. Hydrogen atoms formed first, the simplest possible configuration, one proton, one electron, a partnership that's still the most common arrangement in the universe today. It took 380,000 years of cooling for matter as we know it to become possible. Everything before that was a hot plasma, a soup of particles that couldn't form stable relationships. Perhaps there's a lesson in that. Some things require patience, require the right conditions, require the universe itself to cool down enough to allow complexity to emerge. For its first 380,000 years, the universe was completely opaque. If you could have existed back then, could have opened your eyes, you wouldn't have seen anything. Not because there was no light, there was plenty of light, but because that light couldn't travel freely. It would scatter off the free electrons in the plasma, bouncing around like a photon trapped in an infinite fog. It must have been like being inside a glowing cloud, everything bright, but nothing visible beyond a certain distance. No stars to see, no galaxies, no structure at all. Just this luminous fog extending in every direction. And then, when atoms formed, when electrons found their nuclei and stopped scattering photons, the fog cleared. Light could suddenly travel across space. The universe became transparent for the first time, and if there had been eyes to see it, they would have witnessed something like dawn breaking after an impossibly long night. That first light, now cooled and stretched into microwaves, is still travelling. It's what we detect as the cosmic microwave background, the universe's way of remembering when it first learned to be clear. The universe is expanding, carrying galaxies away from each other like boats drifting on an ocean that's somehow growing larger. But here's the interesting thing. Galaxies within the same cluster, the ones that are close enough to each other, they stay together. Gravity holds them in place, binds them into groups, into neighborhoods. It's a bit like cities staying intact while the space between them grows. Your neighborhood remains your neighborhood, the buildings stay where they are, the streets connect the same places they always did. But the distance to the next city over, that's increasing. The highways stretch longer, the gaps widen, and eventually cities that were once reachable become too far to visit, receding beyond any possible journey. The universe maintains its local structures, clusters of galaxies, gravitationally bound, cosmically neighbourly, even as it pulls those neighbourhoods farther and farther apart. There's something almost melancholy in that. The way proximity preserves relationships while distance inevitably severs them. The Big Bang wasn't an explosion in space. That's the common image. A burst of matter and energy radiating outward from some central point, like fireworks or a bomb. But that's not quite right. The Big Bang was an expansion of space itself. There was nowhere for it to explode into because there was no outside yet, no stage on which the explosion could perform. Imagine the universe as the surface of a balloon, and you're drawing dots on that surface with a marker. As the balloon inflates, the dots move away from each other, not because they're travelling across the balloon surface, but because the surface itself is stretching. That's closer to what happened. Space expanded, and everything in it moved apart as a consequence, not because it was thrown outward, but because the fabric of reality itself was growing. There was no centre to this expansion, no edge, no boundary where the universe stopped and something else began. Just space, creating more of itself everywhere, all at once. Time itself began with the Big Bang. That sentence might settle strangely in your mind, especially if you're used to thinking of time as something that just exists. A river that's always been flowing. But according to our best understanding, time had a beginning too. Before the Big Bang, there was no before. The word loses its meaning when there's no time to measure. This makes questions like, what came before the Big Bang, potentially meaningless. Not because we don't know the answer, but because the question itself might not make sense. It's like asking what's north of the North Pole. The question seems reasonable until you realize that north stops having meaning at that point. Maybe that frustrates you, or maybe there's something freeing in it. The universe doesn't owe us answers that fit comfortably into the categories our minds prefer. Sometimes the answer is that the question dissolves when you look at it closely enough. The universe creates about 275 million new stars every day. That's across all galaxies, all clusters, all the star-forming regions scattered through space. It works out to roughly 3,000 stars being born every second. A constant cosmic nursery, always active, never resting. Think about that for a moment. In the time it takes you to read this sentence, thousands of stars have ignited for the first time, beginning their long burning lives. Some will live for billions of years, some for mere millions. Some will end quietly, others in spectacular explosions that seed the cosmos with heavy elements. But all of them begin the same way. Clouds of gas collapsing under their own gravity, heating up, compressing until the core becomes hot and dense enough for fusion to start. That moment when a star first lights up, when it transitions from a dark cloud to a burning sphere, that's happening right now, and somewhere in the universe, again and again and again. The universe is generous with its stars, wastefully abundant, creating them faster than anyone could ever count. The light from the most distant observable objects has been travelling for over 13 billion years to reach us. 13 billion years. That light began its journey when the universe was young, when the first galaxies were just forming, when space was smaller and hotter and very different from what it is now. We see these objects not as they are, but as they were. By the time their light reaches our telescopes, those distant galaxies have evolved, changed, perhaps even died. We're looking at fossils, in a sense, preserved images of things that existed long ago, frozen at the moment the light left them. It's a strange kind of archaeology, where the deeper you look into space, e.g. the further back you see in time. The universe keeps its history visible, written in light that's still travelling, still carrying information from epochs we can never visit. Maybe you find that comforting, the idea that the past isn't truly gone, just far away, still observable if you have the right instruments and enough patience. Cosmic inflation theory suggests something almost unimaginable. In the very first fraction of a second after the Big Bang, we're talking about a period of time so short that it makes a blink seem like an eternity. The universe doubled in size at least 90 times. At least 90 times. Each doubling happened faster than you can snap your fingers. A region of space smaller than an atom became larger than the observable universe in less time than it takes light to cross the width of a proton. And it's the kind of statement that should sound absurd, and maybe it does. Maybe your mind rejects it as too extreme, too violent, too impossible. But this inflation, this exponential expansion, solves several puzzles about why the universe looks the way it does, why it's so uniform, so flat, so finely balanced. Sometimes the universe's actual history is stranger than anything we dare to invent, and all we can do is follow where the evidence leads, even when it takes us to places that feel more like poetry than physics. The universe has no smell, no sound, no colour in the vacuum of space. All the sensory richness we experience, the scent of rain, the sound of wind, the blue of the sky, these are created by our atmosphere and by our minds, interpreting vibrations and wavelengths. Strip away the air, venture into the void between stars, and there's nothing to carry sound waves, nothing to scatter light into colours, nothing to deliver molecules to your nose. Space is silent. Not quiet, but truly silent. The kind of silence that never ends, that no sound has ever broken. The explosions of supernovae, the collisions of galaxies, the birth cries of stars, all of it happens in absolute stillness. We add the sound effects later, in our documentaries and films, because we can't imagine drama without noise. But the universe doesn't need our imagination. It's content to conduct its most violent events in perfect, eternal quiet. Maybe that changes how you think about the cosmos, not as a place of thunderous activity, but as a vast, silent ballet of matter and energy, playing out across distances and timescales that dwarf human comprehension. Neutron stars are so dense that a teaspoon of their material would weigh about 6 billion tons on Earth. 6 billion tons, a single teaspoon. That's roughly the weight of a mountain compressed into something you could stir your tea with, if the spoon could somehow survive the experience. The universe has found ways to pack matter tighter than anything we can achieve in our laboratories. When a massive star collapses, when it exhausts its fuel and can no longer support itself against gravity, its core compresses beyond what seems possible. Protons and electrons get crushed together, forming neutrons, and those neutrons pack so closely that they're touching, with essentially no space between them. It's matter at its theoretical limit, pressed as tightly as the laws of physics allow before it would collapse further into a black hole. Perhaps it's hard to visualize. How could matter be that dense, that heavy, that compressed? But the universe doesn't ask permission before violating our intuitions. It just does what the equations allow, creating objects so extreme they border on the unbelievable. The universe contains roughly 1 septillion stars. That's a 1 followed by 24 zeros. If you tried to write it out, it would look like this: 1 quintillion. There are more stars in the universe than grains of sand on all of Earth's beaches combined. Every beach, every desert, every handful of sand you've ever touched. Add them all together, count every single grain, and you'd still fall short of the number of stars. Maybe that number feels meaningless because it's too large to grasp. The human mind didn't evolve to comprehend quantities like that. We're good with numbers we can see, can touch, can count on our fingers, but a septillion, that's beyond our natural capacity. And yet each of those stars is real, is burning somewhere in the cosmos, has its own life cycle, its own characteristics. The universe is extravagant with its creations, unconcerned with whether we can comprehend the scale. It just keeps making stars, filling space with them, scattering them so generously that most will never be observed, never be named, never be known by anyone. There's a strange humility in that realization. Empty space isn't truly empty. Even in the darkest void, far from any star or galaxy, quantum fluctuations ensure that particle-antiparticle pairs are constantly appearing and disappearing. They pop into existence, borrowed from the vacuum's energy, live for impossibly brief moments, then annihilate each other and vanish back into nothingness. It's like the vacuum itself is restless, unable to stay completely still, always buzzing with this subtle activity. The universe maintains a gentle hum of creation and annihilation, even in its emptiest regions. These particles exist for such short times that they're called virtual particles, not quite real in the classical sense, but not quite fictional either. They have measurable effects, influence the behavior of atoms and light in ways we can detect and calculate. Even in the darkest void, the universe refuses to be completely inactive. Perhaps there's something comforting in that, the idea that nowhere is truly empty, that even in the loneliest reaches of space something is happening. Some tiny drama of creation and destruction is playing out again and again, forever. And the largest known structure in the universe is something called the Hercules Corona Borealis Great Wall. It spans about 10 billion light years. 10 billion. To put that in perspective, it would take light, travelling at 186,000 miles per second, the fastest thing we know of, 10 billion years to travel from one end to the other. This structure is a collection of galaxy clusters, connected by filaments of matter, forming a wall-like shape across the cosmos. It's so large that it challenges some of our assumptions about how the universe should be organized. According to certain principles in cosmology, structures this large shouldn't exist. The universe hasn't been around long enough for gravity to pull together something so vast. And yet there it is, stretched across a significant fraction of the observable universe, quiet and enormous and impossible to ignore. Maybe the universe doesn't always follow the rules we think we've figured out. Maybe it still has surprises left, structures and patterns we haven't even begun to understand. The universe's expansion rate is measured using something called Hubble's constant, named after Edwin Hubble, who first discovered that the universe was expanding. But here's the thing, scientists still disagree on its exact value. Different measurement methods give different answers, and the discrepancy is large enough that it can't be explained by simple measurement error. This disagreement has a name, the Hubble tension. On one side, you have measurements from the cosmic microwave background, that ancient light from the early universe. On the other side, you have measurements from supernovae and other local cosmic markers. They should agree, but they don't. The difference is small in absolute terms, a few kilometers per second per megaparsec, but it's consistent and unexplained. Maybe it's telling us that our models are incomplete, that there's new physics hiding in this discrepancy. Or maybe it's a measurement issue we haven't identified yet. Either way, it's a reminder that the universe still holds secrets, still refuses to give up all its answers even to our most precise instruments. Photons from the cosmic microwave background have been travelling through space for 13.8 billion years before entering your eye. These particles of light began their journey when the universe first became transparent, when the fog of plasma cleared and light could finally move freely. They've been crossing the cosmos ever since, never stopping, never interacting with much of anything, just travelling. And here's something strange and wonderful. When you see static on an old television, about 1% of that static is this ancient light. The cosmic microwave background is literally part of the noise, mixed in with signals from human broadcasts and electronic interference. You can see the echo of the Big Bang on a screen in your living room, if you know where to look. It's the universe's way of making itself accessible, perhaps, not hiding its earliest moments in some distant, unreachable place, but letting them rain down on us constantly, visible even in the most mundane technology. The oldest light in existence, and it's been here all along, waiting patiently to be noticed. And the universe appears to be expanding in all directions equally from every point. There's no preferred direction, no axis along which expansion happens faster or slower. If you could stand anywhere in the cosmos, on Earth, on a distant galaxy billions of light years away, in the void between clusters, you'd see the same pattern. Galaxies receding in all directions, the farther ones moving away faster, everything expanding uniformly. This property is called isotropy, and it's one of cosmology's most beautiful symmetries. It means the universe doesn't play favourites with locations or directions. There's no cosmic compass pointing towards some special place, no centre from which everything radiates. Wherever you are, you're at the centre of your own observable universe, and the view looks roughly the same. It's a kind of equality built into the fabric of space-time itself. Every observer, regardless of position, sees the same large-scale structure, the same patterns, the same laws of physics at work. Maybe there's something reassuring in that uniformity, or maybe it makes the universe feel more distant, more impersonal. Perhaps it's both at once. Here's a strange little thought experiment. If you could fold a piece of paper 42 times, it would reach the moon. 42 folds. It sounds absurd. Paper is thin, the moon is far away, but the mathematics is clear. Each fold doubles the thickness, and exponential growth becomes powerful very quickly. The first fold takes you from a fraction of a millimetre to twice that. The 10th fold gets you to about the thickness of your hand. The 20th fold reaches about a kilometre. By the 30th fold, you're at 100,000 kilometres, already a quarter of the way to the moon, and by 42 folds you've reached it. The exponential nature of this folding, where each step doubles the previous result, mirrors the exponential expansion of the early universe during inflation. A tiny region of space doubling, then doubling again, then again, growing from subatomic to cosmic in the blink of an eye. It's the same mathematical principle, just applied to space-time instead of paper. Sometimes the universe's most dramatic behaviours can be understood through simple analogies if you know where to look. The first stars, called population 3 stars, were made of almost pure hydrogen and helium. Nothing else existed yet. No carbon, no oxygen, no iron or silicon, or any of the elements that make up planets and people. Just the two lightest elements, the ones created in the Big Bang itself. These stars were massive, much larger than the Sun, burning hot and bright and dying quickly in spectacular supernova explosions. When they died, they scattered the first heavy elements into space, carbon forged in their cores, oxygen created in their final moments, iron produced in the explosion itself. Every heavier element in your body, every atom that isn't hydrogen or helium, was cooked inside stars that came after these first pioneers. The calcium in your bones, the iron in your blood, the carbon that forms the backbone of every molecule in your cells, all of it was created in stellar furnaces and distributed through space by dying stars. You're made of stardust, as the saying goes, but more specifically, you're made of elements that didn't exist for the first few 100 million years of cosmic history. The universe had to age, had to create and destroy generations of stars before it could make something like you. The universe was completely dark for about 100 million years after the Big Bang. This period is called the Dark Ages, though not because anything bad was happening, just because there were no stars yet to produce light. The cosmic microwave background had faded as it cooled and redshifted, and the first stars hadn't ignited yet. Imagine that time, if you can. A universe full of hydrogen and helium, slowly collapsing into clumps under gravity's patient pull, but nothing burning yet. No light sources except the fading glow of the Big Bang itself. It must have been profoundly dark, like darker than the deepest cave or the most remote place on Earth, because even those places have some scattered photons from stars. But in the cosmic dark ages, there were no stars to scatter light from, just darkness and hydrogen and the slow, inexorable gathering of matter into denser and denser clouds, preparing for the moment when the first star would finally light up. It's like a cosmic intermission between acts, the initial glow fading, the first stars not yet ready, and the universe waiting patiently in the dark for the next phase of its story to begin. Gravitational waves ripple through the fabric of space-time itself, carrying information about cosmic collisions. When black holes spiral into each other, when neutron stars merge, when the most violent events in the universe occur, they send these ripples outward at the speed of light, travelling across billions of light years. When these waves pass through Earth, they stretch and squeeze space itself by tiny amounts. Impossibly tiny amounts, less than the width of a proton across distances of several kilometres. We've built detectors sensitive enough to measure these minute distortions, instruments so precise they can detect changes smaller than an atomic nucleus in structures larger than a building. And when we detect these waves, we're not just seeing the aftermath of a collision, we're feeling it. The gravitational waves that pass through the detectors also pass through you, through this room, through everything on Earth, subtly stretching and compressing space-time in a rhythm that matches the death spiral of objects millions or billions of light years away. You're being touched very gently by events of cosmic violence from the distant universe. It's happening right now, has been happening since you were born, will continue long after you're gone. The universe might be infinite in size, or it might loop back on itself like the surface of a sphere. Current measurements can't distinguish between these possibilities. Both scenarios fit the data equally well within the margin of error. This is one of those fundamental questions about reality that remains genuinely open. If the universe is infinite, then it contains infinite matter, infinite stars, infinite galaxies, extending forever in all directions with no boundary, no edge, no place where space stops. If it loops back on itself, then you could, in principle, travel in one direction long enough and eventually return to your starting point, even though the distances involved would be so vast that even light wouldn't complete the journey within the current age of the universe. Both possibilities are strange in their own ways. Infinity is hard to grasp. The idea that there's always more, that you could never reach an end no matter how far you travelled. But a finite universe that loops is equally odd. Where would you be when you return to your starting point? Would you meet yourself? Maybe the universe is content being undecided, or maybe we just don't have the right tools yet to measure which version is true. quantum mechanics suggests something even stranger than usual, if that's possible. According to one interpretation, the many worlds interpretation, the universe might split into parallel versions every time a quantum measurement is made, and every time a particle's state is determined, the universe branches, creating separate realities for each possible outcome. If this interpretation is correct, then the cosmos is unimaginably larger than we observe. Every quantum event spawns new universes, and there are quantum events happening constantly, everywhere, in every atom, every photon, every interaction between particles. The number of parallel universes would grow exponentially, faster than you could count, creating a multiverse so vast that our entire observable universe would be just one branch among countless others. Maybe there's a version of you in one of those branches who made different choices, lived a different life. Maybe there are versions where history went differently, where stars formed in different patterns, where the laws of physics have subtle variations. Or maybe this interpretation is wrong, and quantum mechanics doesn't work that way at all. The equations don't tell us which interpretation is correct, they just describe what happens, leaving us to wonder about the implications. The cosmic web shows that galaxies aren't randomly distributed throughout space. They form filaments and walls around giant voids, creating a structure that looks remarkably organic when you map it out. From far enough away, if you could somehow view the entire observable universe at once, it would resemble neural networks in a brain or the branching patterns of biological tissue. These filaments are streams of galaxies connected by threads of dark matter, flowing along invisible highways carved by gravity over billions of years. The voids between them are vast, hundreds of millions of light years across in some cases, regions where almost no galaxies exist, where space is emptier than empty. It's like the universe organized itself into a foam, with matter clustering along the bubble walls and vast hollows in between. No one designed this structure, no intelligence planned it. It emerged naturally from the initial conditions of the Big Bang, from tiny fluctuations in density that grew over time, guided by gravity's patient pull. The universe builds cathedrals without architects, creates art without artists, organizes itself into patterns that echo structures we see in completely different contexts. Maybe that's coincidence, or maybe it's telling us something deeper about how complexity emerges from simple rules. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. That's the travel time for photons to cross the 93 million miles between our star and our planet, moving at the speed of light the entire way. It's not a long time in cosmic terms, but it means something interesting. We never see the sun as it is right now. When you look up at the sun, you're seeing it as it was 8 minutes and 20 seconds ago. If something dramatic happened on the solar surface right this moment, a massive flare, an eruption, anything, we wouldn't know about it for another 8 minutes. We're always looking at the past, even when we look at the closest star. The present sun is hidden from us, separated by the time it takes light to cross the space between us. In a way, we're time travelers every time we look up, seeing events that have already happened, or that are already in the past by the time the light reaches our eyes. The universe has no now that's shared across distance, only a collection of different pasts arriving at different times depending on how far the light has travelled. The cosmic microwave background has patterns in it, tiny variations in temperature, small ripples in the ancient light, and these patterns serve as a kind of standard measuring stick. They tell us the size of the universe when that light was emitted, and by comparing that to how large those same patterns appear today, we can calculate how much space has expanded in the intervening time. These patterns are called acoustic oscillations, sound waves that rippled through the early universe when it was still hot and dense enough for pressure waves to travel through it. The sound has long since faded. There's no medium for it to travel through anymore, but the imprint remains, frozen into the distribution of matter, visible in the cosmic microwave background as slightly warmer and cooler regions. It's like the universe left us a ruler, a cosmic yardstick embedded in its own structure, allowing us to measure distances across billions of light years with surprising precision. We're using the echoes of sound waves from when the universe was 380,000 years old to map the cosmos today. It's an elegant solution to an otherwise impossible problem. How do you measure something when you can't reach out and touch it, when even light takes billions of years to make the journey? Redshift tells us how fast distant galaxies are moving away from us. When an object moves away, its light gets stretched toward longer wavelengths, toward the red end of the spectrum. The faster it recedes, the more extreme the redshift. It's the cosmic version of the Doppler effect, the same principle that makes an ambulance's siren sound different as it approaches and then drives away. By measuring how much a galaxy's light has been redshifted, we can calculate its velocity, and by comparing that velocity to its distance, we can map the expansion of the universe. The farthest galaxies show the most extreme redshifts. Their light stretch so much that ultraviolet wavelengths from their stars appear as infrared by the time they reach us. Some are receding so fast that they are approaching the speed of light, carried away by the expansion of space itself. We'll never be able to visit them, never send signals that could reach them. Yeah, because the space between us is growing faster than light can cross it. They're slipping beyond a horizon, one by one, disappearing not because they're dying, but because space itself is carrying them away. The universe is vast and it's getting vaster, and there are places that were once visible that will eventually fade from view entirely, lost not to distance but to the inexorable expansion that pulls everything apart. The universe's first molecules were hydrogen molecules, formed about 100,000 years after the Big Bang. Before that, there were only individual atoms, hydrogen and helium, floating freely, too energetic to bond with each other. But as the universe cooled, as the temperature dropped, atoms could finally pair up, forming the simplest possible molecule. Two hydrogen atoms bonded together. Chemistry couldn't begin until this moment. Atoms have to stick together, have to form partnerships and structures before you can have molecules, compounds, the building blocks of anything complex. For the first 100,000 years, the universe was too hot for chemistry. It was a place of physics only, particles and energy, but no chemical reactions, no molecular structures. And then it cooled just enough, and the first molecules formed, and suddenly a new kind of complexity became possible. It's a small step, perhaps, from individual atoms to pairs of atoms, but it's also the first step toward everything that would come later: water molecules, carbon chains, the organic compounds that eventually led to life. The universe had to learn how to be cool before it could learn how to be interesting. Cosmic rays are high-energy particles that constantly rain down on Earth from across the universe. They're mostly protons, accelerated to nearly the speed of a light by processes we don't fully understand. Supernova shockwaves, maybe, or magnetic fields near black holes, or something else entirely. They travel across the galaxy, sometimes across the universe, for millions or billions of years before reaching Earth. When they strike the upper atmosphere, they create cascades of secondary particles, showers of fragments that spread out and fall toward the surface. Some of those particles reach the ground. Some pass through you right now as you're lying there. You're being hit by cosmic rays constantly. Particles that might have originated in a supernova explosion thousands of light years away, and us or in a galaxy cluster billions of light years distant. The most energetic ones, the ultra-high energy cosmic rays, have energies so extreme that we still don't know what could possibly accelerate them. They hit the atmosphere with the energy of a well-thrown baseball, concentrated into a single subatomic particle. It's absurd, impossible, and yet it happens. The universe creates particles we can barely explain, sends them flying across space for eons, and they arrive here, tiny messengers from violent events in the distant cosmos. The universe has been expanding for 13.8 billion years, and according to our current understanding, it will likely expand forever. There's no cosmic rewind button, no moment when gravity will pull everything back together, no big crunch to mirror the Big Bang. The expansion will continue, driven by dark energy, accelerating as time goes on. In this scenario, the universe's future is one of increasing isolation. Galaxy clusters will drift apart until they're no longer visible to each other. Stars will exhaust their fuel and die, one by one, until no new stars form because all the available gas has been used up. Eventually, trillions of years from now, the universe will be dark, cold, and empty, with burned-out stellar remnants drifting alone in an ever-expanding void. It's called the heat death, or sometimes the big freeze, and it's about as melancholy as cosmic scenarios get. But it's also unimaginably distant so far in the future that the current age of the universe is just a brief moment in comparison. Maybe there's comfort in that, the idea that endings, even cosmic ones, are so far away that they're almost abstract. Or maybe you find it unsettling, this vision of inevitable decline. Either way, it's what the evidence currently suggests, though dark energy could still surprise us with unexpected behaviour. The Planck epoch refers to the first 10 to the power of minus 43 seconds after the Big Bang. That's a decimal point followed by 42 zeros and then a 1, an inconceivably brief moment, shorter than any time interval we can currently measure or meaningfully describe. During this epoch, the universe was so hot, so dense, so extreme that our current physics breaks down completely. At this scale, quantum effects and gravity merge in ways we don't yet understand. We have quantum mechanics with a very small and general relativity for gravity and large-scale structure. But they don't play nicely together, don't combine into a single coherent theory. So when we try to describe the Planck epoch, when both quantum effects and gravitational effects are equally important, our equations fail. They give infinite answers, meaningless results, or just stop working altogether. It's a reminder that our understanding, however sophisticated, has limits. There are regimes where nature operates according to rules we haven't discovered yet, perhaps can't discover with current tools. The universe's earliest moment remains beyond our reach, not because we lack instruments, but because we lack the theoretical framework to even ask the right questions. The universe has perfect amnesia about what might have existed before the Big Bang. Cosmic inflation, that exponential expansion in the first fraction of a second, erased any information about previous states. If there was something before, another universe, a different configuration of space-time, anything. Inflation smoothed over the evidence, stretched it out so thoroughly that nothing survived to tell the tale. It's like taking a wrinkled sheet and pulling it tight from all sides until the wrinkles disappear. Whatever patterns existed before are gone, erased by the stretching. The universe we observe emerged from inflation without memory, without fossils from a previous state. Maybe there was nothing before. Maybe the Big Bang truly was the beginning of everything. Or maybe there was something, but we've lost all access to it, all information about it obliterated by the universe's own expansion. We're left in a cosmos that only remembers its own history back to a certain point, beyond which everything is speculation, untethered from evidence. Perhaps that's frustrating, or perhaps there's something peaceful in it. The idea that the universe started fresh, unburdened by whatever came before. Antimatter is matter's mirror twin. For every particle, there's an antiparticle, identical in mass but opposite in charge. An electron has a positively charged anti-electron called a positron. A proton has a negatively charged antiproton. When matter and antimatter meet, they annihilate, converting completely into energy with perfect efficiency. The strange thing is that the Big Bang should have created equal amounts of matter and antimatter. The physics suggests perfect symmetry. For every particle created, an antiparticle should also appear. But if that happened, if matter and antimatter were created in equal amounts, they would have annihilated each other completely, leaving the universe empty except for radiation. No atoms, no stars, no galaxies, no you. Something broke the symmetry. Somehow, the universe preferred regular matter over antimatter by just 1 part per billion. For every billion antimatter particles, there were 1,000,000,001 matter particles. After the annihilation, that tiny excess was all that remained, and it's what built everything we see. We don't know why this asymmetry exists, what process favored matter, what caused the imbalance. It's one of physics' deepest mysteries. Why does the universe exist at all instead of being empty radiation? The answer is hidden somewhere in those first moments, in some asymmetry we haven't identified yet. The observable universe contains roughly 10 to the power of 80 atoms. That's a 1 followed by 80 zeros, a number so large that if you tried to count them, giving each atom 1 second of your time, you'd need more time than the universe has existed, multiplied by trillions upon trillions. There are more atoms in the universe than seconds that have passed since the Big Bang, even if you multiply those seconds by billions. Every breath you take contains about 10 to the 22nd power atoms. That's 10,000 billion atoms entering and leaving your lungs with each inhale and exhale. The human body itself contains roughly 7 times 10 to the 27th power atoms, give or take, depending on your size. So you personally are made of less than a trillionth of a trillionth of a trillionth of the atoms in the observable universe. You're an infinitesimal fraction of the cosmic inventory, a tiny collection of matter that happens to be organized in a way that can think about atoms, can contemplate the universe, where it can wonder about its place in the vast scheme of things. Maybe that makes you feel small, or maybe it makes existence feel more precious. The fact that out of all those atoms, some small number of them arrange themselves into you. Cosmic voids of vast regions of space with very few galaxies, sometimes stretching hundreds of millions of light years across. They're the universe's great empty halls, places where galaxy formation somehow failed, where matter never coalesced into the bright structures we see elsewhere. If you could travel through a void, you'd wait eons between neighbours, crossing distances so vast that even the concept of loneliness seems inadequate. These voids aren't completely empty. There's still dark matter, still some scattered gas, still the cosmic microwave background radiation filling space. But in terms of galaxies, in terms of stars and visible structure, they're as close to nothing as the universe gets. And here's what's interesting. These voids are growing. Because they have less matter than average regions, they have less gravity pulling things together, which means the expansion of space affects them more strongly. The emptiest places in the universe grow emptier still, the voids expanding faster than the filaments between them. It's a kind of cosmic inequality, where the rich regions get richer in galaxies and the poor regions get poorer, driven not by any conscious process but by the simple mathematics of gravity and expansion working together over billions of years. The universe's density is about 6 protons per cubic meter on average. 6 protons. A cubic meter is about the size of a large refrigerator, and on average, across all of space, there are only 6 protons in that volume. For comparison, the air you're breathing right now contains about 10 to the 25th power molecules per cubic meter. That's 10 trillion molecules in the same space where the cosmic average is just 6 protons. Space is far emptier than the best vacuum we can create on Earth. Our finest laboratory vacuums still contain billions of particles per cubic meter. The interstellar medium, the gas between stars, contains maybe 1 atom per cubic centimeter, still vastly denser than the cosmic average. Space, true cosmic space averaged over the entire universe, is mostly nothing. The matter that does exist, all the stars, all the galaxies, all the gas and dust, is concentrated into tiny pockets, islands of density in an ocean of emptiness. We live on one of those islands surrounded by matter, protected by an atmosphere, and we sometimes forget just how unusual that is. How rare it is to be somewhere dense enough to support structure, let alone life. Quasars are among the brightest objects in the universe. They're powered by supermassive black holes at the centers of distant galaxies, black holes that are actively feeding, consuming entire stars and vast clouds of gas. As matter spirals into the black hole, it heats up to millions of degrees, radiating tremendous amounts of energy before crossing the event horizon and disappearing forever. A single quasar can outshine an entire galaxy of hundreds of billions of stars. Think about that for a moment. One object, one black hole's accretion disk, producing more light than 100 billion suns combined. The brightest quasars are visible across billions of light years, beacons from the early universe when galaxies were younger and black holes fed more voraciously. We see them as they were long ago, when the universe was still in its adolescence, still violent and active in ways it no longer is. Most quasars have faded now, their black holes having exhausted the nearby supply of matter to consume. The ones we observe are fossils in a sense, images of an era that's past preserved in light that's been travelling toward us for most of cosmic history. By the time their light reaches us, the quasars themselves have likely gone quiet, their black holes dormant, waiting in the dark centres of galaxies that have grown old and settled into quieter rhythms. The universe creates heavy elements only in stellar furnaces and cosmic explosions. Hydrogen and helium were made in the Big Bang, but everything heavier, carbon, nitrogen, oxygen, iron, gold, all of it required stars. Stars fuse lighter elements into heavier ones in their cores, building up the periodic table step by step through nuclear reactions that release energy and keep the star shining. But stars can only go so far. Elements up to iron can be created in normal stellar fusion, but anything heavier requires even more extreme conditions. Supernova, the explosive deaths of massive stars, create some of these heavier elements in the violence of their final moments. Neutron star collisions create others, smashing matter together with such force that even the heaviest elements form. Every gold atom in a wedding ring was forged in one of these cataclysmic events, either in a supernova explosion or in the collision of two neutron stars. The universe doesn't make gold gently, doesn't create platinum or uranium through patient processes. It requires violence, extreme temperatures, incredible densities, conditions that only exist in the most dramatic events the cosmos can produce. You wear the remnants of cosmic catastrophes on your finger, carry the debris of stellar deaths in your jewelry, in your electronics, in your bones. The cosmic microwave background has tiny temperature variations across the sky, fluctuations of only about 0.00001 degrees Celsius. That's 10,000ths of a degree, variations so small that it took decades of increasingly sensitive instruments to map them accurately. But these whisper-quiet fluctuations were the seeds that grew into all the cosmic structure we see today. Regions that were slightly denser than average, even by this tiny amount, had slightly more gravity. That extra gravity pulled in more matter, which created even more gravity, which pulled in even more matter, in a feedback loop that grew over billions of years. Those microscopic fluctuations in the early universe became galaxy clusters, superclusters, the cosmic web itself. The pattern we see in the cosmic microwave background, that subtle mottling, those barely there variations, that's the blueprint for everything that came after. It's like seeing the plans for a building before construction begins, except the building is the entire large-scale structure of the universe, and the construction took 13.8 billion years. The universe didn't start smooth and then become lumpy by accident. The lumpiness was there from the beginning, written into the temperature of space itself. He's just waiting for gravity to amplify it into galaxies and stars. The universe's geometry determines its fate. If space curves inward on itself, like the surface of a sphere, then eventually the expansion will slow, stop, and reverse, leading to a big crunch where everything collapses back together. If space curves outward like a saddle, then it will expand forever, accelerating until everything is isolated and cold. If space is perfectly flat, it sits on the knife's edge between these possibilities. Current evidence suggests we live in a flat universe, or at least one so close to flat that we can't measure the difference. And with dark energy driving acceleration, the future looks like eternal expansion. Galaxies eventually becoming unreachable islands in an ever-growing void. It's strange to think that the shape of space itself determines whether the universe will end in fire or ice, collapse or expansion, whether everything will one day come back together or drift apart forever. Geometry isn't just mathematics on a chalkboard, it's the structure of reality, and that structure has consequences that play out over cosmic timescales. Maybe billions of years from now, if any consciousness still exists, they'll watch the last stars flicker out, knowing that the universe chose expansion, chose isolation, chose the long, cold fade instead of the violent reunion. Cosmic acceleration was discovered in 1998 by observing distant supernovae. Astronomers expected to measure how much the universe's expansion was slowing down. After all, gravity should be pulling everything back together, at least a little bit. No, but when they measured carefully, when they looked at supernova billions of light years away, they found something unexpected. The universe wasn't slowing down, it was speeding up. This discovery was shocking enough to earn a Nobel Prize. It upended our understanding of the universe's fate, introduced the concept of dark energy, and raised questions we're still trying to answer. Why is the expansion accelerating? What's driving it? Dark energy is the name we've given to whatever's responsible, but the name doesn't explain anything. It's just a label for our ignorance. The supernovae appeared dimmer than they should have been, which meant they were farther away than expected, which meant space had expanded more than it should have if expansion were slowing down. From that one observation, this dimness, this subtle discrepancy in brightness, we learned that the universe's future is not what we thought, that there's an energy permeating space that pushes against gravity, that the cosmos has surprises left even after a century of modern cosmology. The universe has a horizon beyond which light hasn't had time to reach us yet. This cosmic horizon isn't a physical barrier. There's nothing there, no wall or edge. It's just a boundary of observation, a limit imposed by the finite age of the universe and the finite speed of light. Beyond that horizon, galaxies exist, stars shine, matter moves, but their light hasn't completed the journey to Earth yet. As the universe ages, this horizon expands. New regions come into view. Galaxies that were previously beyond our observational reach suddenly appear as their light finally arrives. Yeah, we're constantly seeing the universe for the first time in a way. Not because it's changing dramatically, but because light from distant places is still in transit, still travelling across the expanding space between us. But there's also a complication. Because space is expanding, some regions that are currently beyond our horizon will never become visible, even given infinite time. They're receding faster than their light can approach us, carried away by the expansion of space itself. So while our horizon expands in one sense, there are parts of the universe that will remain forever out of reach, forever beyond the boundary of what we can observe. The universe is larger than what we can see, and it's getting larger faster than we can catch up. Baryonic matter, the ordinary stuff we're made of, the atoms and molecules and particles that make up everything we can directly observe, accounts for less than 5% of the universe's total energy. 5%. Everything else is dark matter and dark energy, substances we've never directly detected, that we know about only through their gravitational effects and their influence on cosmic expansion. We're a tiny minority component in a cosmos dominated by things we've never touched, never seen, never isolated in a laboratory. It's a humbling realization. The stars you see at night, the planets, the gas clouds, the galaxies stretching across billions of light years, all of that visible splendor represents just a small fraction of what's actually out there. Most of the universe is invisible to us, composed of dark matter that doesn't emit or absorb light, permeated by dark energy that pushes space apart without clustering into any structure we can map. Maybe you find that unsettling, this idea that we're surrounded by invisible presences, that most of reality operates in modes we can't directly access. Or maybe there's something comforting in the mystery, in knowing that the universe still has secrets, still holds depths we're only beginning to explore. Either way, it's a reminder that what we see isn't all there is, that the visible universe is just the surface of something much larger and stranger. The universe may have undergone multiple phase transitions as it cooled, like water freezing into ice. These weren't gentle changes. They were fundamental shifts in the nature of reality itself, moments when the laws of physics transformed into something different. In the earliest moments, when temperatures were unimaginably high, forces that are now separate might have been unified into a single force. As the universe cooled, these forces split apart, first gravity separating from the others, then the strong nuclear force, then the electromagnetic and weak forces dividing. Each transition was a breaking of symmetry, a moment when the universe chose one configuration over others that were equally possible at higher temperatures. It's a bit like a ball sitting perfectly balanced on top of a hill. As it rolls down, it has to pick a direction, and once it does, that choice is locked in. The universe picked directions during its phase transitions, and those choices determine the fundamental constants, the particle masses, the strength of forces, everything that makes physics work the way it does today. If the transitions had gone differently, if the ball had rolled in another direction, the universe might have ended up with completely different laws. Perhaps electrons would have different masses, or gravity would be stronger, or atoms couldn't form at all. We live in the universe that resulted from those early choices, whatever they were. Cosmic strings, if they exist, would be defects in space-time thinner than a proton but stretching across galaxies. They'd be scars from the universe's earliest moments, frozen imperfections left over from phase transitions in the first fraction of a second after the Big Bang. Imagine a crack in ice that forms when water freezes. Cosmic strings would be similar, except the ice is the fabric of space-time itself. These strings would have extraordinary properties. Despite being thinner than an atom, they'd be incredibly massive. A cosmic string 1 centimetre long might weigh as much as Mount Everest. They'd curve space-time around them, creating gravitational effects detectable across vast distances. If one passed between us and a distant star, we'd see double images of that star, light bent around the string from both sides. We've searched for these signatures, looked for the telltale patterns that cosmic strings would create, but haven't found any yet. Maybe they don't exist. Maybe they're too rare to have crossed our line of sight, or maybe they're there but we haven't looked carefully enough. Either way, the idea persists that the universe might still carry scars from its birth, defects in reality itself, stretching invisibly through space waiting to be discovered. The universe's expansion means that galaxies beyond about 15 billion light-years will eventually become forever unreachable. Even if we could travel at the speed of light, even if we had infinite time, we could never catch galaxies receding faster than light through expanding space. They're not moving through space faster than light, which would violate relativity, but space itself is expanding between us and them, carrying them away. It's a strange kind of horizon, not a place you could visit, but a boundary in possibility itself. There are galaxies we can see today, can photograph, can study, that are already beyond this boundary. Their light is still reaching us, having left billions of years ago when they were closer, but no signal we send now will ever reach them. If we pointed a laser at one of these distant galaxies, the light would travel outward forever, crossing incredible distances, but never catching up because the space ahead of it is expanding faster than the light can cross it. The universe has partitioned itself into regions that can communicate and regions that can't, and the boundary between them is constantly shifting, constantly claiming new galaxies that slip beyond the edge of reach. We're watching them recede in slow motion, knowing that eventually their light will redshift so much it becomes undetectable and they'll fade from view entirely, not because they died, but because space grew too large between us. The cosmic neutrino background contains neutrinos created just seconds after the Big Bang. They decoupled from other matter when the universe was only 1 second old, slipping free from the dense plasma that filled space, and they've been travelling ever since. About 300 million of these ghostly particles pass through your body every second. You don't feel them because neutrinos barely interact with matter. They could pass through light years of solid lead, and most of them wouldn't stop, wouldn't even slow down. They're called ghost particles for good reason, present everywhere, influencing almost nothing. But they carry information from the universe's first second, from a time when space was so hot and dense that even neutrinos couldn't escape. We've never detected the cosmic neutrino background directly. They're too low energy, too elusive, but we know they're there, predicted by the same physics that gives us the cosmic microwave background, filling space with a sea of particles from the earliest moments of time. Right now, as you lie there, you're being permeated by messengers from the Big Bang, particles that have been travelling through the universe for 13.8 billion years, passing through planets and stars and galaxies without noticing, without caring, just streaming onward at nearly the speed of light. The universe appears the same in all directions, isotropic, and looks the same at all locations when averaged over large enough scales, homogeneous. This property, called the cosmological principle, is one of the foundational assumptions of modern cosmology. It says that there's nothing special about our location, no preferred direction in space, no centre where things look different. On small scales, this obviously isn't true. Earth is different from the void between galaxies. Our solar system is different from a supernova. But zoom out far enough, the average over hundreds of millions of light years, and the variations smooth out. The distribution of galaxies becomes uniform. The cosmic microwave background looks the same no matter where you point your telescope. It's this uniformity, this sameness, that allows us to apply physics consistently across cosmic distances. If every region of space operated by different rules, if the laws of nature varied from place to place, we'd have no hope of understanding the universe as a whole. But the cosmological principle says that physics works the same everywhere, that an electron here behaves like an electron in a galaxy billions of light years away, that gravity operates by the same equations regardless of location. It's a kind of cosmic equality. Every place is fundamentally like every other place, at least on average, at least when you step back far enough to blur the details. Gravitational lensing bends light around massive objects, letting us see galaxies that would otherwise be hidden. When light from a distant galaxy passes near a massive cluster of galaxies in the foreground, the cluster's gravity curves space-time, and that curvature bends the light's path. The result is that we can see around corners, in a sense, observe objects that are directly behind other objects from our perspective. Sometimes the lensing creates multiple images of the same galaxy, stretched and distorted into arcs or rings. The most dramatic examples look almost artificial, like someone arranged cosmic magnifying glasses in space to show us things we shouldn't be able to see. But it's all natural, all just gravity doing what gravity does, curving space-time, and light following those curves. Einstein predicted this effect, though he thought we'd never be able to observe it because the distortions would be too subtle. But the universe provides its own telescopes, its own lenses, massive enough to magnify distant galaxies and bring them into view. We've learned to use these natural lenses, searching for galaxy clusters positioned just right to magnify whatever lies behind them, essentially getting free magnification from the cosmos itself. The universe is helping us explore itself, providing tools we never had to build. The universe's critical density is the exact amount of matter and energy needed to make it geometrically flat. Not curving inward like a sphere, not curving outward like a saddle, just flat. It's about 5 atoms of hydrogen per cubic meter on average. Measurements show we're incredibly close to this critical value, perhaps exactly at it within the margin of error. This is strange because there's no obvious reason the universe should be so close to flat. If the initial density was even slightly higher than critical, the universe would have curved strongly inward, might have collapsed back on itself billions of years ago. If the initial density was slightly lower, space would curve outward and expansion would have proceeded so fast that galaxies could never form. The window for ending up with a flat universe is narrow, and yet that's apparently where we are. Inflation theory explains this by proposing that the early exponential expansion stretched space so thoroughly that any initial curvature was flattened out, like pulling a wrinkled sheet tight until you can't see the wrinkles anymore. But it's still remarkable. Of all the possible universes with all the possible densities and curvatures, we find ourselves in one that's balanced right at the critical point, right on the knife's edge between different geometric destinies. Cosmic inflation predicts that the universe should be full of primordial gravitational waves from its first moments. These waves would have been created by the violent expansion itself, ripples in space-time generated when the universe doubled in size again and again in that first tiny fraction of a second. They'd still be travelling through space, stretched by expansion but never disappearing, carrying information from the earliest moment we can theoretically observe. Detecting these primordial gravitational waves would be like hearing the universe's birth cry echoing through space-time. We'd be observing the first 10 to the power of minus 35 seconds of cosmic history, a time when the universe was smaller than an atom when inflation was just beginning. These waves would leave a distinctive pattern in the cosmic microwave background, a swirl in the polarization of that ancient light. Experiments have searched for this signal, building telescopes at the South Pole and in the Atacama Desert, places where the atmosphere is clear enough to measure these subtle effects. So far we haven't found them, or rather, we found hints that turned out to be dust, foreground contamination, false alarms. But the search continues, because finding primordial gravitational waves would confirm inflation. These would give us direct observational access to the universe's first moment, would let us see farther back in time than we've ever seen before. It would be cosmology's holy grail, assuming the waves exist and we can separate them from everything else in the data. The universe creates about 10 new stellar mass black holes every day from dying massive stars. Somewhere in the cosmos, roughly every 2 hours, a star's core collapses past the point of no return, compressing matter so thoroughly that not even light can escape. These are the quiet black holes, not the supermassive ones at galaxy centers that make headlines, but stellar remnants, the gravitational ghosts of stars that once burned bright. When a massive star exhausts its fuel, when fusion stops and there's nothing left to hold the core up against gravity's pull, it collapses. If the star is massive enough, this collapse doesn't stop at a neutron star, it keeps going, crushing matter past the density of atomic nuclei, past any point where known physics can describe what's happening, until a black hole forms. The outer layers might explode as a supernova, might scatter heavy elements into space, but the core is gone, compressed into a region of curved space-time so extreme that it's effectively cut off from the rest of the universe. 10 of these form every day, on average. Most we'll never detect, never observe, because they're too far away or not actively consuming matter, or just lost in the vast spaces between galaxies. But they're there, accumulating slowly, adding to the universe's population of objects from which nothing escapes. The cosmic distance ladder uses different measurement techniques like overlapping rungs on a ladder to map the universe. For nearby objects, we use parallax, the apparent shift in position as Earth orbits the Sun, the same effect that makes your finger seem to move against the background when you close one eye and then the other. For objects farther away, we use Cepheid variables, stars whose brightness fluctuates in predictable ways that tell us their intrinsic luminosity. For even greater distances, we use supernovae, cosmic standard candles that let us measure billions of light years. Each method reaches farther but depends on the accuracy of the previous step. If we get parallax wrong, we get Cepheid distances wrong, which means supernova distances are wrong, which means our map of the entire universe is wrong. One, it's a delicate chain of calibration, each link relying on the one before it, stretching from our solar neighbourhood all the way to the edge of the observable universe. And there are gaps, jumps between rungs where we're not entirely sure the overlap is perfect. The Hubble tension, that disagreement about how fast the universe is expanding, might come from a problem somewhere in this ladder, some systematic error we haven't identified. Or it might be telling us that the universe doesn't quite work the way we think it does, that there's new physics hiding in the discrepancy. Either way, it's a reminder that our cosmic distance measurements are hard-won, carefully constructed, and potentially fragile if any rung turns out to be weaker than we thought. Again, the universe's earliest light we can see comes from when it was only 380,000 years old, about 0.003% of its current age. That's the cosmic microwave background, the moment when space became transparent and light could finally travel freely. Everything before that is hidden from direct observation, not because we lack the technology, but because light itself couldn't escape the dense plasma that filled space. We see farther back in time than forward. The observable past, 13.8 billion years of cosmic history, dwarfs any conceivable future we'll witness. Even if humanity survives for millions of years, we'll only observe an infinitesimal fraction of cosmic time compared to what's already visible in the sky. Every photon from the cosmic microwave background is older than the oldest stars, older than the first galaxies, older than anything except the universe itself. When you detect that radiation, and it's all around you, passing through you constantly, you're touching something from when the cosmos was still in its infancy, still cooling from the initial heat, still settling into the structure it would maintain for billions of years. The past is more accessible than the future, at least in cosmology. We can look back and see the universe at different ages, but we can only imagine forward, only extrapolate, only guess at what will come. Cosmic microwave background photons outnumber atoms by about 1 billion to 1. For every particle of matter, every proton, every neutron, every electron, there are roughly 1 billion photons from the Big Bang filling space. Matter is rare, radiation is common, the universe is overwhelmingly made of light, at least in terms of particle count. This ratio tells us something important about the early universe. Matter and antimatter must have been nearly balanced, with matter winning by just 1 part per billion. After matter and antimatter annihilated each other, converting to photons, that tiny excess of matter was all that remained, and it's everything we see. All the atoms in all the galaxies, in all the stars and planets and dust clouds, all of it came from that 1 in a billion surplus. The photons from the annihilation are still here, cooled to microwave wavelengths, outnumbering the surviving matter by the same ratio that matter originally exceeded antimatter. It's a fossil record written in particle statistics, a reminder that the universe we inhabit is the remnant of a nearly perfect cancellation, saved from emptiness only by the slimmest of margins. The universe's fundamental constants, like the speed of light, the gravitational constant, the charge of the electron, appear to be the same everywhere we look. Light from distant galaxies shows the same spectral lines as light produced in laboratories on Earth, which means atoms work the same way there as they do here. Gravity seems to operate by the same equations billions of light years away as it does in our solar system. This uniformity is remarkable when you think about it. There's no obvious reason the constants have to be the same across such vast distances and timescales. They could vary with location, could drift over time, could be different in regions we can't observe. But all the evidence suggests they don't change. The universe plays by consistent rules, and those rules apply everywhere, everywhen. If these values were even slightly different, if the strength of gravity changed by a few percent, if the electromagnetic force was a bit stronger or weaker, stars wouldn't form, atoms would be unstable, chemistry as we know it would be impossible. The universe sits in a narrow range of parameter space where complex structure can exist, where stars can burn for billions of years, where planets can form and persist. Maybe that's just luck, or maybe there's something deeper at work, some selection effect or fundamental principle that requires the constants to have the values they do. Either way, we're fortunate, or inevitable, depending on your perspective, to exist in a universe that's finely tuned enough to allow existence at all. The anthropic principle suggests the universe must have properties that allow observers to exist within it. This isn't as circular as it might sound. The idea is simple. We can only observe a universe compatible with our existence. If the constants were different, if the laws of physics didn't allow stars or atoms or chemistry, there'd be no observers to notice. So in a sense, the universe had to be capable of producing observers, because otherwise we wouldn't be here asking why it has the properties it does. There are different versions of this principle. The weak version just notes that our existence constrains what we can observe. We necessarily find ourselves in a universe that can support life. The strong version suggests the universe must have properties that inevitably lead to observers. And then there are multiverse interpretations, where countless universes exist with different constants, and we happen to be in one of the rare ones where observers are possible. It's a cosmic selection effect. We're sampling from the subset of possible universes that can support beings capable of asking questions about the universe. Maybe you find this satisfying, or maybe it feels like avoiding the question. Either way, it's a reminder that our existence and the universe's properties are entangled in ways that make some questions difficult to separate from the fact that we're here to ask them. The universe might be part of a vast multiverse, with different regions having different physical laws. In eternal inflation models, the exponential expansion that shaped our observable universe might still be happening elsewhere, so creating pocket universes that bud off and evolve independently. Each pocket could have different constants, different particles, different forces, a different set of physical laws determined by how fields settle into their lowest energy states during that region's formation. Our universe might be just one bubble in an infinite foam of cosmic possibilities. Some bubbles might be stillborn, collapsing immediately because their constants don't allow stable matter. Others might expand forever, but remain empty because stars can't form, and a few, perhaps very few, might have conditions right for galaxies, stars, planets, life. We'd be in one of those rare bubbles, not because we're special, but because those are the only ones that can contain observers. The multiverse is speculation, of course. We can't observe other universes by definition, can't test the hypothesis directly, but it emerges naturally from some theories of inflation, from quantum mechanics' many worlds interpretation, from string theory's landscape of possible vacuum states. Maybe it's real, or maybe it's just mathematics running ahead of physics, extrapolating beyond what we can ever verify. The question might be fundamentally unanswerable, which is either frustrating or liberating depending on your temperament. Cosmic reionization occurred when the first star's light stripped electrons from hydrogen atoms throughout the universe. For hundreds of millions of years after the Dark Ages, space was filled with neutral hydrogen, atoms with electrons bound to their nuclei, not interacting much with passing light. But when the first stars ignited, when their ultraviolet radiation began flooding space, it had enough energy to knock electrons free again. This was the universe's renaissance in a way, the moment when starlight transformed the character of intergalactic space. The universe had been neutral, opaque to certain wavelengths, and it became ionized, transparent in new ways. This wasn't instantaneous or uniform. Stars formed in clumps, in the densest regions, so reionization proceeded in bubbles that grew and merged over millions of years. Eventually the bubbles overlapped, and the entire universe was reionized, though the process wasn't complete until the universe was about 1 billion years old. We can study this era by looking at the spectra of distant quasars, reading the absorption lines left by neutral hydrogen clouds, watching how those clouds disappear as we look at later epochs. It's cosmic archaeology. We're reading history in the signatures of long-gone neutral gas, reconstructing the timeline of when and how the first stars changed the universe they were born into. The universe's large-scale structure formed through gravitational collapse over billions of years. Tiny quantum fluctuations from the Big Bang, variations in density at the smallest scales, created by quantum uncertainty during inflation, were stretched to cosmic sizes and became the seeds for everything that followed. Regions slightly denser than average pulled in more matter, became denser still, pulled in even more matter in a feedback loop that ran for billions of years. First, dark matter collapsed into halos, creating gravitational wells that ordinary matter fell into. Then gas clouds formed within those halos, cooled, fragmented, began forming stars. Those stars grouped into galaxies. Galaxies merged and clustered. Clusters connected into filaments. And gradually, over cosmic time, the tiny fluctuations visible in the cosmic microwave background grew into the massive structures we see today. Clusters containing thousands of galaxies, filaments, hundreds of millions of light years long, voids emptier than the average. The universe started nearly smooth and became lumpy through the patient action of gravity, amplifying tiny differences until they became overwhelming. It's a reminder that given enough time, even the smallest advantages compound, Even the smallest initial conditions can lead to dramatic outcomes. The universe builds its cathedrals one small accretion at a time, guided by mathematics, shaped by initial conditions that were set in the first fraction of a second. The cosmological constant first proposed by Einstein represents the energy density of empty space itself. Einstein introduced it to make his equations predict a static universe. The prevailing belief at the time was that the cosmos was eternal and unchanging. When Hubble discovered the universe was actually expanding, Einstein called the cosmological constant his biggest blunder and removed it from the equations. But the cosmological constant came back. When we discovered cosmic acceleration in 1998, when we realized something was pushing galaxies apart, the simplest explanation was to reintroduce Einstein's discarded term. It turns out empty space might have energy, might exert a kind of negative pressure that drives expansion. Whether this is literally the cosmological constant or something more complicated called dark energy is still debated, but the effect is real. Space has weight, in a sense, has an energy density that affects how the universe evolves. And the value of this constant, if it is constant, is incredibly small compared to what particle physics predicts. The mismatch between prediction and observation is one of physics' biggest embarrassments, a discrepancy of 120 orders of magnitude, which is either the worst theoretical prediction ever or a sign that we're missing something fundamental about how quantum fields and gravity interact. Either way, Einstein's blunder might have been his most prescient idea, a term he introduced for the wrong reasons that turned out to be necessary after all. The universe's baryon asymmetry problem asks why matter exists at all, when matter and antimatter should have annihilated completely. The physics we know says that the Big Bang should have created equal amounts of particles and antiparticles. When they met, they should have destroyed each other entirely, leaving only radiation. But obviously that didn't happen. We exist. Matter exists. The universe is full of protons and electrons that never found their antimatter partners. Some unknown process favoured matter by just 1 part per billion, enough to build everything we see. After the annihilation, that tiny excess remained, became the atoms in stars and planets, became us. We don't know what caused this asymmetry, what physics allowed matter to win. There are theories, violations of certain symmetries, exotic particles in the early universe, and processes that worked slightly differently for matter versus antimatter, but no definitive answer. It's one of the great unsolved problems in cosmology. The universe's existence depends on an imbalance, on a tiny preference for matter over antimatter, and we don't know why that preference exists. Maybe it was built into the initial conditions, maybe it emerged from physics we haven't discovered yet, or maybe it's just luck, a random fluctuation that happened to go our way. Without that imbalance, you wouldn't be here reading this. The universe would be empty photons, no structure, no complexity, no one to wonder why. Cosmic variance means our observable patch might not be representative of the universe as a whole. We can only see so far, limited by the speed of light and the age of the universe, and our observable bubble might just happen to be unusual in some way. Maybe we're in a region that's slightly denser than average, or slightly less dense. Maybe the large-scale structure around us isn't typical of what exists beyond our horizon. This is a real concern for cosmology. We only have one universe to observe, and we can only see part of it, so we're drawing conclusions about cosmic properties from a single, possibly unrepresentative sample. It's like trying to understand Earth's climate by measuring the weather in one city. You might happen to pick a city that's unusually hot or cold, wet or dry, and your conclusions would be skewed. Cosmic variance is especially important for measuring rare, large-scale structures. If you're studying something that only happens once per observable universe, you can't tell if it's truly rare or if you just happen to have one nearby. We account for this statistically, estimate the uncertainty introduced by having limited data, but the fundamental limitation remains. We might live in an unusual neighborhood, cosmically speaking, and we'd have no way to know unless we could somehow observe multiple independent patches of the universe. Maybe that makes our conclusions less certain, or maybe it's just another reminder that science works with the data available, making the best inferences possible given the constraints. The universe's metallicity increases over time as stars create and disperse heavy elements. In astronomy, metals means anything heavier than hydrogen and helium, carbon, oxygen, iron, everything else. The first stars had essentially zero metallicity, whole made only of the primordial elements from the Big Bang. But when those stars died, they enriched the space around them with the elements forged in their cores and in their explosive deaths. The cosmos grows chemically richer with age, enabling planets and eventually life. Each generation of stars forms from gas that's slightly more metal-rich than the previous generation. Our Sun is a third-generation star, maybe fourth, formed from a cloud already enriched by countless stellar deaths. The Earth itself, the iron in its core, the silicon in its crust, the oxygen in its atmosphere, none of that existed in the early universe. It took billions of years of stellar nucleosynthesis, billions of supernovae, uncounted stellar deaths to create the raw materials for rocky planets. The universe had to mature before it could build worlds like ours. Maya had to accumulate the chemical diversity that makes complex chemistry possible. In the early universe, planets would have been impossible. There was nothing to build them from except hydrogen and helium, which don't form solid surfaces. We live in a universe old enough to have manufactured the periodic table, patient enough to have distributed those elements widely enough for planets to form from them. The Sunyaev-Zeldovich effect shows how cosmic microwave background light scatters off hot gas in galaxy clusters. When photons from the ancient background radiation pass through these clusters, some of them collide with high-energy electrons in the hot intracluster gas. These collisions boost the photons to higher energies, shifting them slightly in the spectrum we observe. This creates cosmic shadows, for in a sense, regions where the cosmic microwave background appears slightly different because galaxy clusters are in the way. It's not a shadow in the usual sense of blocking light, but rather a distortion, a subtle change in the spectrum that reveals the presence of hot gas. The effect is named after the physicists who predicted it in the 1960s, long before we had instruments sensitive enough to detect it. Now we use it to find galaxy clusters, to measure their masses, to map the distribution of hot gas that fills the space between galaxies in these massive structures. It's remarkable that we can see galaxy clusters not by their stars or their galaxies, but by how they affect light that's been travelling since the universe was 380,000 years old. The cosmic microwave background serves as a backlight, and anything between us, and it leaves its fingerprint on the ancient glow. The universe might eventually enter a big freeze, where expansion makes everything cold, dark, and isolated. In this scenario, the cosmos doesn't end with a bang. No collapse, no crunch, no violent finale, but with an eternal whisper that slowly fades toward absolute zero. galaxies drift apart until they can no longer see each other. Stars exhaust their fuel and die. No new stars form because all the available gas has been consumed or dispersed too thinly. Eventually, after timescales that make the current age of the universe seem like a blink, 10 to the 14th power years, 10 to the 20th power years, incomprehensibly far in the future, even the longest-lived stars burn out. Galaxies become graveyards of stellar remnants, white dwarfs, neutron stars, black holes, neat objects that no longer generate energy, that just radiate away their remaining heat into the expanding void. The universe grows darker, colder, emptier. Black holes evaporate through Hawking radiation, though this takes 10 to the power of 100 years or more depending on their mass. Eventually even the black holes are gone, and what remains is a cold, diffuse soup of particles and radiation at a temperature infinitesimally above absolute zero, expanding forever, growing colder still, approaching, but never quite reaching, perfect emptiness. It's melancholy when you think about it, this vision of cosmic decline, but it's also so distant, so far beyond any timescale we can meaningfully contemplate, that it feels more like mathematics than fate. Cosmic time dilation means distant galaxies' clocks appear to run slower when we observe them. And this is a consequence of both the expansion of space and general relativity. Time itself is stretched along with the light travelling through expanding space. When we observe a supernova in a distant galaxy, it appears to brighten and fade more slowly than a nearby supernova would. Distant supernovae take longer to reach peak brightness, longer to fade, the timescale stretched by the same factor that redshifts their light. Time itself ran slower when the universe was younger and denser, or rather, it runs slower from our perspective when we look at those distant epochs. It's not that the supernovae actually exploded in slow motion. To an observer near the supernova, everything would have appeared normal. But from our vantage point, billions of years later and billions of light years away, the entire event appears stretched out in time. The universe was younger when that light was emitted, space was smaller, and clocks, all clocks, including the internal clock of a supernova's explosion, ticked at a different rate relative to our time now. It's another reminder that time isn't absolute, isn't the same everywhere, that observations depend on the relationship between observer and observed, on the expansion of space itself, on the structure of space-time through which information travels. The universe creates most of its new stars in massive bursts rather than steadily over time. Star formation peaked about 10 billion years ago and has been declining ever since. When the universe was 3 to 4 billion years old, stars formed at a rate 10 times higher than today. Galaxies were younger, had more available gas, collided and merged more frequently, triggering bursts of star formation in the chaos. Now, in the universe's middle age, things have settled down. Most of the easily available gas has been consumed or locked up in stars. Galaxy collisions are less frequent. Star formation continues, but at a gentler pace, a slow decline that will continue into the future. Eventually, in hundreds of billions of years, the last stars will form from the last reservoirs of hydrogen, and then star formation will cease entirely. The universe had a peak, a golden age of stellar creation, and we're living in the long decline afterward. Perhaps that's fitting. The most dramatic, creative, violent era is in the past, and what remains is a slower, quieter epoch, where the structures built during that peak gradually age and fade. The universe is settling into its old age, not dead but less vigorous, are less productive, content to maintain what's already been built rather than creating vast amounts of new structure. The cosmic light horizon limits how far we can ever see, regardless of how long we wait. It's not just about distance, it's about the combination of distance and cosmic expansion. There are regions of space receding so fast that their light will never reach us, even given infinite time, even if we wait trillions of years, even if we're patient beyond any reasonable measure. Those regions remain forever beyond our observational reach. Parts of the universe are slipping away, crossing a boundary from observable to unobservable, not because they're dying or changing, but because space itself is expanding too quickly. Light from these regions is emitted in our direction, is travelling toward us at the speed of light, but the space between us and them is growing faster than the light can cross it. It's like running on a treadmill that's going faster than you can run. You're moving forward, but you never get closer to your destination. The cosmic horizon is constantly claiming new galaxies, new regions of space that were once observable but are now too far, receding too fast, lost to the expansion. And there's nothing we can do about it except watch them go, their light red shifting into invisibility, their contribution to the observable universe fading away. The universe is larger than what we can see, and the gap is growing. The universe's first galaxies were much smaller and irregular compared to the grand spirals we see nearby. These cosmic toddlers were scrappy, chaotic. Arms formed from the first collections of stars that gravity managed to pull together. They didn't have the elegant spiral arms of the Milky Way, the smooth elliptical shapes of the largest galaxies today. They were messy, clumpy, actively forming stars at rates that would consume their gas supplies in a fraction of the time modern galaxies take. These early galaxies merged and grew over billions of years into the mature galaxies we observe today. Small galaxies collided and combined. Gas flowed inward, settled into disks, organized itself through rotation and gravity into more orderly structures. The process was violent but constructive, building larger and larger systems through accumulation and collision. The universe started with small irregular star collections and built upward, combining them into grander structures, smoothing them through mergers and time into the diverse population of galaxies we see across different epochs. When we look at distant early galaxies, we're seeing this process underway. Galaxies still in their formative stages, still chaotic, not yet settled into the configurations they'd eventually achieve. And when we look at nearby galaxies, we're seeing the mature results, billions of years of evolution, and mergers later, the final products of that long assembly process. Cosmic voids expand faster than average regions because they have less matter to slow expansion. Gravity works both ways. It doesn't just pull matter together in dense regions, it also means that underdense regions feel less gravitational restraint, allowing expansion to proceed more freely. The emptiest places in the universe grow emptier still, these voids expanding faster than the filaments between them. It's a kind of cosmic inequality where the rich get richer and the poor get poorer, driven not by any conscious process but by the simple mathematics of gravity and expansion, working together over billions of years. Matter flows out of voids along the gravitational gradients that connect them to surrounding filaments. The voids grow and merge, creating ever larger empty regions, while the filaments maintain or even increase their density as matter accretes onto them. The universe is becoming more structured over time, more contrasted. The dense regions denser, the empty regions emptier, the gap between them widening. It's a natural consequence of gravitational instability, the tendency for small variations in density to amplify themselves over time. And maybe there's something inexorable about it, this cosmic sorting process that separates the universe into crowded neighborhoods and vast deserts. Or maybe it's just gravity doing what gravity does, patient and implacable, never stopping, always pulling matter together in some places while leaving other places increasingly alone. The universe might have extra dimensions beyond the three of space and one of time we experience. String theory, one approach to unifying quantum mechanics and gravity, suggests there could be as many as 10 or 11 dimensions total. Most of them will be curled up, compactified into shapes smaller than atoms, invisible to our senses and instruments. Imagine a garden hose viewed from far away. It looks like a one-dimensional line, but an ant walking on it would discover a second dimension, thus the circular cross-section of the hose wrapped around the length. Extra dimensions in string theory would work similarly, present but wrapped up so small that we don't perceive them directly. These dimensions could affect particle physics, could explain why forces have the strengths they do, could provide space for strings, the fundamental objects in string theory, to vibrate in different modes that appear to us as different particles. It's speculative, of course. We have no direct evidence for extra dimensions, no experimental confirmation, but the mathematics works beautifully, unifying aspects of physics that seem incompatible in 4 dimensions. Maybe the universe is larger in a literal sense than we perceive, not just spatially extended but dimensionally richer, says with hidden directions that matter and energy can move through in ways we haven't detected yet. The cosmic web's filaments channel matter like rivers, feeding galaxy clusters at their intersections. Dark matter forms the skeleton of these filaments, creating gravitational channels that ordinary matter follows. Gas flows along these highways, pulled by gravity toward the densest regions, where it pools and forms galaxies. The structure isn't random. It's organized by gravity into efficient pathways that connect voids to filaments to clusters. These filaments can stretch hundreds of millions of light years, thin threads of dark matter and gas connecting the largest structures in the universe. Where filaments intersect, you find the richest galaxy clusters, massive collections of thousands of galaxies held together by their combined gravity. The web is dynamic, still evolving, still channeling matter along its threads. Gas continues to flow, galaxies continue to fall along the filaments toward clusters, the structure growing and changing even now. If you could watch the universe in fast forward, speeded up so that billions of years passed in seconds, you'd see this web emerge from near uniformity. Watch as gravity carved structure from smoothness, as matter flowed along invisible highways of dark matter, building the cosmic architecture we observe today. The universe builds its own infrastructure, creates its own road network, all through the patient action of gravity shaping matter over cosmic time. The universe's vacuum energy remains constant even as space expands, unlike matter and radiation that dilute. When space grows larger, the amount of matter per cubic meter decreases. The same atoms are spread over more volume. Radiation dilutes even faster because its wavelengths stretch with expansion, losing energy. But vacuum energy, if it truly is the cosmological constant, doesn't dilute at all. Every cubic meter of newly created space carries the same energy density as every existing cubic meter. As the universe expands, creating more space, it's also creating more dark energy in total. This might sound like it violates conservation of energy, and in a sense it does. Or rather, energy conservation doesn't work quite the way you'd expect in an expanding universe. General relativity doesn't guarantee global energy conservation when space-time itself is dynamic. The vacuum energy of space is an intrinsic property, and as space grows, that property comes along for the ride. This means dark energy becomes increasingly dominant as the universe ages and stretches. Matter and radiation become more and more diluted, but dark energy maintains its density, so eventually, and we're already approaching this point in cosmic history, dark energy becomes the dominant component, the primary driver of how the universe evolves. It's a strange kind of substance, this vacuum energy, gaining influence simply by refusing to diminish while everything else thins out. Cosmic magnetic fields permeate space, though much weaker than Earth's, affecting how matter moves through the universe. These fields aren't as strong as the ones around planets or stars. They're millions or billions of times weaker, but they exist nearly everywhere, threading through galaxies, filling the spaces between them, aligned along the cosmic web's filaments. They might have been seeded in the early universe, tiny magnetic fields generated by some process in the first moments after the Big Bang, then stretched and amplified by cosmic expansion and by the motions of charged particles over billions of years. Or they might have been created later, by the first stars, by supernovae, by processes in galaxies that expelled magnetized gas into intergalactic space. We're still piecing together the history, still trying to understand how these fields got there and how they have evolved. But they have consequences. They affect how cosmic rays travel, bending the paths of charged particles as they move through space. They influence how gas falls into galaxies, how it organizes itself within them. They might even play a role in regulating star formation, yet in transporting energy and angular momentum in ways that gravity alone can't explain. The universe has magnetic structure layered on top of its gravitational structure, an invisible web of aligned fields that threads through the visible matter, subtle but pervasive. The universe's matter distribution shows patterns matching those predicted by quantum fluctuations from inflation. The ripples we see in the cosmic microwave background, the way galaxies cluster on large scales, the statistical properties of cosmic structure, all of it matches what you'd expect if inflation took tiny quantum fluctuations and stretched them to cosmic sizes. It's remarkable when you think about it. The large-scale structure of galaxies, filaments spanning hundreds of millions of light years, might be magnified quantum noise from the first fraction of a second. Quantum mechanics usually operates at the smallest scales, atoms, particles, subatomic processes. But inflation provides a mechanism to take those tiny fluctuations, those unavoidable uncertainties in quantum fields, and blow them up to scales larger than galaxy clusters. The uncertainty principle operating at 10 to the power of minus 35 seconds after the Big Bang becomes the blueprint for where galaxies form 13.8 billion years later. It's a connection between the very small and the very large, between quantum mechanics and cosmology, that nobody expected before inflation was proposed. Maybe you find that beautiful, the idea that the cosmic web traces its ancestry to quantum foam, that the pattern of galaxies in the sky preserves information about quantum fields from the universe's first instant. Or maybe it just seems improbable, too neat, too elegant. Either way, the data supports it. The predictions match the observations, and we're left contemplating a universe whose largest structures remember its smallest beginnings. The cosmic star formation rate peaked when the universe was about 3 billion years old. That was the epoch of maximum stellar production, when galaxies were forming stars at the highest average rate, when the universe was at its most active in converting gas into stars. Since then, for the past 10 billion years, the rate has been gradually declining. The universe has been winding down its star factories, slowly but steadily, as the available fuel gets consumed and the conditions for prolific star formation become less common. Galaxies have used up much of their easily accessible gas. Major mergers, which trigger bursts of star formation, happen less frequently as the universe expands and galaxies spread farther apart. The decline isn't rapid, isn't catastrophic, just a gentle downward trend that's expected to continue indefinitely. We're living in the universe's long afternoon, perhaps, past the peak of stellar creativity, watching the rate slowly drop as the cosmos ages. In the far future, star formation will become rare, then very rare, then eventually cease entirely when the last reservoirs of hydrogen are exhausted. But that's trillions of years away, so distant that the current epoch, even with its declining star formation, still seems vibrant by comparison. The universe isn't dying, not yet. It's just past its prime, settling into a quieter phase where creation continues but at a more measured pace. The universe's smoothness problem asks why regions too far apart to have ever communicated look so similar. Without inflation, there are parts of the observable universe separated by such distances that light hasn't had time to travel between them even once since the Big Bang. They couldn't have exchanged information, couldn't have equilibrated, couldn't have coordinated to have the same temperature, the same density, the same properties, and yet when we look at the cosmic microwave background, when we measure the temperature in opposite directions of the sky, we find that it's the same to within 1 part in 100,000. How did these regions know to be at the same temperature if they've never been in contact? Inflation solves this by proposing they were once close enough to communicate, to equilibrate, before inflation stretched them far apart. During inflation's exponential expansion, regions that were initially in thermal contact were separated by distances so vast that light hasn't had time to cross between them since. The universe looks smooth because it was smooth before inflation, and inflation preserved that smoothness while stretching it across scales far larger than light could travel. It's an elegant solution to a genuine puzzle. Why is the universe so uniform when causality suggests different regions should have evolved independently? The answer, if inflation is correct, is that they didn't evolve independently. They started in contact, achieved equilibrium, and then were separated faster than light could travel between them. Cosmic bubble collisions, if they occurred, might have left circular patterns in the cosmic microwave background. In eternal inflation models, different bubble universes can nucleate and expand, and occasionally bubbles might collide while both are still inflating. The collision would leave a distinctive signature, a circular region in the cosmic microwave background with slightly different temperature patterns, a bruise in the sky from where our universe bumped into a neighbour. Finding such patterns would be extraordinary. It would be direct observational evidence that our universe collided with another universe during its infancy, that the multiverse isn't just theoretical speculation, but physical reality with measurable consequences. Researchers have searched for these signatures, analysed the cosmic microwave background looking for anomalous circles, and so far haven't found any convincing candidates. Maybe bubble collisions are too rare. Maybe they didn't happen during the observable patch of our inflation, or maybe the entire scenario is wrong and bubbles don't collide in ways that leave detectable marks. But the possibility remains that somewhere in the cosmic microwave background data, if we look carefully enough, we might find evidence of another universe, a cosmic neighbour we briefly touched before expanding apart forever. It would rewrite our understanding of what the universe even means, transforming it from everything that exists to just our local bubble in a much larger multiverse structure. The universe's thermal history shows a clear cooling trend from infinitely hot to the frigid 2.7 Kelvin we measure today, and temperature and time are intimately linked in cosmology. Colder always means older, at least when you're talking about the average temperature of space itself. The universe started in a state of extreme heat and has been cooling ever since, energy spreading out over ever larger volumes as space expands. In the first moments, temperatures were so high that fundamental forces were unified. Particles we consider distinct today were indistinguishable from each other. As the universe cooled, forces separated, particles acquired mass, different physical regimes emerged. At 10 to the power of 15 Kelvin, the electroweak force split into electromagnetism and the weak force. At 10 to the power of 13 Kelvin, quarks combined into protons and neutrons. At 10 to the power of 9 Kelvin, nuclear synthesis created the first light elements. At 3000 Kelvin, atoms formed and light could travel freely. Each threshold in temperature marked a transition, a change in what was possible, what could exist stably, and the cooling continues. In the far future, if the universe expands forever, the temperature will approach, but never quite reach absolute zero, asymptotically declining toward perfect cold as space stretches toward infinite size. The universe's story is a story of cooling, of energy spreading out and becoming less concentrated, of heat death approaching in slow motion over timescales that beggar imagination. The cosmic coincidence problem asks why dark energy's density is similar to matter's density in the current epoch. For most of cosmic history, this wasn't true. In the early universe, matter and radiation dominated completely. Dark energy was negligible. In the far future, dark energy will dominate overwhelmingly. Matter and radiation will be diluted to insignificance. But right now, in this particular era, they're roughly comparable. Of all times in cosmic history, we happen to live when these two components, matter and dark energy, have similar densities, when neither completely dominates. That seems like an odd coincidence, unless there's some mechanism that links them, some reason why they should be comparable at a particular epoch. Or maybe it's not a coincidence at all. Maybe it's selection bias. Perhaps intelligent observers can only arise during the epoch when these densities are similar, when the universe is old enough for stars to have formed but young enough that structure formation hasn't completely ceased. If dark energy dominated earlier, galaxies might never have formed. If matter dominated longer, perhaps observers couldn't exist for other reasons. It's another anthropic argument, suggesting that we find ourselves at this particular time because this is when observers can exist, and we're necessarily among the observers. Maybe that's satisfying, or maybe it feels like circular reasoning. The coincidence remains either way, that we live in the brief cosmic era when dark energy and matter are comparably important. The universe's curvature is measured to be flat within 0.4% precision by studying the cosmic microwave background. The patterns in that ancient light, the size of hot and cold spots, the statistical distribution of temperature variations, depend on the geometry of space. By mapping these patterns carefully, we can measure whether space curves inward, outward, or remains flat. The answer, within measurement uncertainty, is flat. Space appears to have zero curvature, meaning parallel lines never meet or diverge, meaning triangles have angles that sum to exactly 180 degrees even when the triangles are billions of light years across. This is remarkable for several reasons. First, there's no obvious requirement that space be flat. It could have any curvature. Second, inflation predicts flatness, so this measurement supports inflationary theory. Third, the flatness is so precise that it suggests either we live in a truly infinite universe, or space is curved but on scales much larger than we can observe, so large that the curvature is negligible within our observable patch. Either way, it tells us something fundamental about the universe's geometry, about the shape of space itself. The cosmos chose simplicity. In this respect at least, the simplest possible geometry, flat and Euclidean, at least as far as we can measure. Cosmic strings might create characteristic patterns of duplicated galaxies if their gravitational lensing catches light. A cosmic string passing between us and a distant galaxy would bend light from both sides, creating two images of the same galaxy, offset by a small angle. The images would be identical, same redshift, same structure, same spectral features, because they're both photons from the same source, just taking different paths around the string. Astronomers search for these cosmic fingerprints, looking through galaxy catalogues for pairs that seem suspiciously similar, that might be duplicate images rather than genuinely separate galaxies. So far, no confirmed detections, though there have been candidates that turned out to be false alarms. Maybe cosmic strings don't exist, or maybe they're too rare, the probability of one crossing our line of sight to any particular galaxy too low to have happened yet. But the search continues, because finding a cosmic string would be extraordinary. Direct evidence of a topological defect in space-time, a relic from the earliest moments of cosmic history, a prediction from grand unified theories that's become observational fact. It would open a window into physics at energy scales we can never hope to reach in particle accelerators, using the universe itself as the laboratory, searching for its own scars and imperfections left over from the violent transitions of its infancy. The universe's entropy increases over time, this making it progressively more disordered despite gravity creating structure. This seems paradoxical at first. How can the universe become more disordered when we see galaxies forming, stars condensing from gas clouds, complex structures emerging from simpler beginnings? But entropy and structure aren't opposites in the way you might think. When a gas cloud collapses to form a star, when galaxies assemble from diffuse matter, these processes release enormous amounts of energy as heat and radiation. That dispersed energy represents a huge increase in entropy, more than enough to offset the decrease in entropy from the matter becoming more organized. The universe as a whole becomes more disordered even as local pockets become more structured. Black holes are entropy reservoirs, storing disorder in ways we're still trying to fully understand. Their event horizons contain entropy proportional to their surface area. Vast amounts of entropy hidden behind the boundary where light can't escape. The universe started in a very low entropy state at the Big Bang, highly ordered in a specific way, and it's been sliding toward higher entropy ever since, following the second law of thermodynamics on cosmic scales. Eventually, in the far future, the universe will reach maximum entropy, a state of perfect equilibrium where nothing interesting can happen anymore, where all energy is dispersed uniformly and there's no available gradient to drive any process. But that's so distant, so far beyond any timescale we can meaningfully grasp, that it feels more like a mathematical endpoint than a real future. The cosmic neutrino background has a temperature of about 1.95 Kelvin, slightly cooler than the photon background at 2.7 Kelvin. These neutrinos decoupled from other matter even earlier than photons did, about 1 second after the Big Bang, when the universe was still hot enough for neutrinos to interact frequently, but beginning to cool to the point where they could slip free and travel independently. Since then, they've been streaming through space, cooling along with the cosmic expansion, preserving information from the first second of cosmic history. We've never detected the cosmic neutrino background directly. These neutrinos are so low in energy, so reluctant to interact with anything, that our current detectors can't catch them. It would require technology we don't yet have, sensitivity beyond what we can currently achieve. But we know they're there, predicted with confidence by the same physics that gives us the cosmic microwave background, filling space with about 300 particles per cubic centimetre. They're everywhere, passing through you constantly, ghosts from the universe's first second, carrying information about conditions when space was unimaginably hot and dense. Someday, perhaps, we'll develop detectors sensitive enough to map the cosmic neutrino background, to see the universe as it was at 1 second old instead of 380,000 years old. That would push our observational window closer to the beginning, revealing a younger, hotter, denser cosmos than we've ever directly observed. The universe might be a hologram, with all its three-dimensional information encoded on a two-dimensional surface at cosmic scales. The holographic principle suggests that the information content of any region of space is proportional to the area of its boundary, not its volume. This seems absurd. How could three-dimensional space, filled with galaxies and stars and all the complexity we observe, be fundamentally two-dimensional? But the mathematics works, emerging from studies of black hole entropy and quantum gravity. Black holes have entropy proportional to their surface area, not their volume, which hints that information might be stored on boundaries rather than in bulk. String theory produces holographic dualities, where a theory in higher dimensions is exactly equivalent to a different theory in lower dimensions. Perhaps reality has fewer dimensions than it appears. The three spatial dimensions we experience somehow emerging from deeper physics that operates in 2 dimensions. It's speculative, far from proven, but taken seriously by physicists working on quantum gravity. Maybe you find this disturbing, the idea that depth, volume, the third dimension itself might be an illusion, a convenient description that emerges from something flatter and simpler. Or maybe there's something elegant in it, the way a hologram encodes 3-dimensional information in a 2-dimensional medium. The universe might work similarly. Reality might be holographic all the way down, with everything we experience being a projection from some lower dimensional boundary we can't directly perceive. The cosmic initial conditions were set with extraordinary precision. Tiny changes would make stars impossible. The density of the early universe had to be incredibly close to the critical density for structure to form at all. Too high, and the universe would have collapsed back on itself before stars could form. Too low, and expansion would have been so rapid that matter could never clump together enough to create galaxies. The strength of the nuclear forces had to be in a narrow range for stars to burn stably. for nucleosynthesis to create the elements necessary for chemistry. The ratio of dark matter to ordinary matter had to be appropriate for galaxies to form, but not so extreme that structure formation happened too quickly or too slowly. Change any of these parameters by a few percent, and the universe becomes inhospitable to life, perhaps even to stable stars. Whether this fine-tuning reflects design, necessity, or selection from a multiverse remains one of cosmology's deepest questions. Maybe these values had to be what they are for reasons we don't understand yet, some underlying principle that requires this particular configuration. Maybe we're in one universe among countless others, and we find ourselves here because these are the conditions that allow observers to exist. Or maybe it's just luck, a cosmic accident that happened to produce a universe where complexity can arise, where stars shine for billions of years, where planets can form and persist and perhaps give rise to life. The question touches on physics, philosophy, probability, and meaning in ways that science alone might not be able to resolve. The universe's age can be calculated from its expansion rate, matter content, and the cosmic microwave background temperature. Yet multiple independent methods converge on the same answer, 13.8 billion years, which gives us confidence that we've got it roughly right. We measure the Hubble constant by observing how fast galaxies recede. We measure the cosmic microwave background and use its properties to infer the universe's age. We study the oldest stars and determine how long they've been burning. All these approaches, using different physics, different observations, different assumptions, agree within their error bars. That's rare in science. Usually when you measure something in completely different ways, you get tensions, discrepancies, hints that your models are incomplete. But for the age of the universe, the methods agree. The cosmos is 13.8 billion years old, give or take a few 100 million years depending on measurement uncertainties. It's old enough for stars to have lived and died multiple times over, for galaxies to have formed and evolved, for the universe to have changed from hot and dense to cool and sparse, but young enough that the most massive stars from the first generation have only recently died, that the cosmic microwave background is still detectable, that we can see back to a time when the universe was very different from today. We live in a universe old enough to be interesting, but young enough that its history is still accessible to observation. Cosmic sound waves in the early universe left imprints we can measure in galaxy clustering today. These baryon acoustic oscillations were pressure waves that travelled through the hot plasma before atoms formed, ripples spreading at nearly half the speed of light until the universe cooled enough for atoms to appear and the waves froze in place. Those frozen ripples became slight enhancements in the density of matter, preferred scales where galaxies would later form. When we map the distribution of galaxies across billions of light years, we can see this scale imprinted in the clustering. There's a characteristic distance, about 500 million light years, where galaxies are slightly more likely to be separated. It's subtle, requires surveying millions of galaxies to detect, but it's there, a fossil from when the universe was 380,000 years old, preserved in the pattern of galaxies that formed billions of years later. We use these baryon acoustic oscillations as standard rulers, cosmic measuring sticks that stretch back nearly to the Big Bang. Because we know how large the sound waves were when they froze, we can use their apparent size at different epochs to measure how much space has expanded, calibrating our distance measurements across cosmic time. The universe embedded its own rulers in its structure, left breadcrumbs we can follow back to understand how expansion has proceeded over billions of years. The universe's far future might see protons themselves decay, dissolving even atoms after 10 to the 34th power years or more. Protons are stable as far as we can tell. None has ever been observed to decay spontaneously, but some grand unified theories predict that protons should eventually decay, just over timescales so enormous that we'd never see it happen in laboratory experiments. If this occurs, if protons eventually fall apart into lighter particles and radiation, then the cosmos would ultimately consist only of radiation and black holes. Even the atoms in stellar remnants, in planets, in neutron stars, would eventually dissolve, breaking down into particles that don't form stable matter, and then, over even longer timescales, 10 to the power of 100 years or more, the black holes themselves would evaporate through Hawking radiation, slowly radiating away their mass until they too disappear in final bursts of energy. What would be left is a cold, dark, diffuse sea of particles and radiation at temperatures infinitesimally above absolute zero, expanding forever, approaching but never reaching perfect emptiness. It's the ultimate endpoint if current physics is correct, though we're extrapolating over timescales so vast that predictions become speculative. Still, it's what the equations suggest, that matter itself isn't eternal, that even protons might decay, that the universe's final state is not frozen matter, but the faint echoes of long-vanished structure, expanding into darkness without end. The cosmic variance between different observable universes in a multiverse could be enormous. If eternal inflation is correct, if bubble universes are constantly forming in an inflating background, then each bubble could have different low-energy physics, different fundamental constants, different particles and forces. Our universe might be typical of this ensemble, or it might be extraordinary, or anywhere in between. We have no way to know. We can only observe our bubble, our patch of the multiverse. We can't see other universes by definition. They're beyond our cosmic horizon. We're separated by regions of eternally inflating space that we can never cross. If many universes exist, the variance between them could be vast. Some might be simple, containing only photons and no matter. Others might be complex in ways we can't imagine, with different numbers of spatial dimensions, different force hierarchies, different evolutionary paths. Our universe, with its particular mix of constants that allow stars and atoms and complexity, might be rare or common or unique. There's no way to determine our position in that distribution. Maybe that's frustrating, the idea that we might be part of a larger ensemble, but can never verify it, never compare ourselves to other universes to see if we're typical. Or maybe there's freedom in it, the knowledge that our universe, whatever its status in a hypothetical multiverse, is the one we have, the one we can explore and understand and wonder about. The universe's expansion can be described by a single elegant equation called the Friedmann equation. It links the universe's curvature, expansion rate, and energy content in a beautiful mathematical relationship that fits on one line. Despite the complexity of the cosmos, the trillions of galaxies, the vast structures, the billions of years of evolution, the expansion itself follows this surprisingly simple rule. The equation relates how fast space is expanding to how much stuff it contains and what shape it has. Plug in the density of matter, dark energy and radiation, specify the curvature, and out comes the expansion rate at any given time. You can run it forward to predict the future, run it backward to reconstruct the past. trace the entire history of cosmic expansion with a single mathematical expression. It's derived from general relativity, from the equations Einstein wrote down describing how matter curves space-time apply to a universe that's uniform and isotropic on large scales. The fact that something so simple can describe something so vast that you can summarize the entire expansion history of the universe in one equation speaks to the fundamental elegance of physics, the way complex phenomena can emerge from simple underlying rules. The universe doesn't need complicated mathematics to evolve. It just follows this equation and everything else, the formation of structure, the evolution of galaxies, the changing temperature and density over billions of years, emerges as consequences. The universe continues to surprise us with each new observation, reminding us how much remains unknown. Every answer raises new questions. Every discovery reveals deeper mysteries. We've learned extraordinary things about the cosmos, its age, its composition, its history, its probable future. We've mapped galaxies billions of light years away, detected gravitational waves from colliding black holes, measured the universe's geometry with impressive precision, and yet we still don't know what dark matter is, what dark energy is, whether the multiverse exists, why the constants have the values they do. What happened before the Big Bang, if before even makes sense? We don't know if life exists elsewhere, how common planets like Earth are, whether consciousness is unique to our world or scattered throughout the cosmos. These aren't failures of science. They're frontiers, invitations to keep exploring. Yeah, keep questioning, keep pushing the boundaries of what we understand. Maybe that's the most wonderful thing about the universe. Not just what we've discovered, but what we haven't. Not just the answers we've found, but the questions that remain. It keeps cosmology eternally young despite studying the oldest thing that exists. Every generation of astronomers finds new puzzles, new phenomena that don't fit existing theories, new reasons to look up at the sky and wonder. And maybe that's exactly as it should be. A universe rich enough, strange enough, vast enough that we'll never run out of things to learn, never reach a point where all the questions are answered and all the mysteries solved. We've travelled together through 100 facts about the universe, from its earliest moments to its distant future, from the smallest quantum fluctuations to the largest structures spanning billions of light years. The cosmos is strange and beautiful, more mysterious than we can fully grasp, yet accessible to our curiosity and our instruments. Perhaps what's most remarkable is that we can understand any of it at all, that creatures on a small planet orbiting an ordinary star in an unremarkable galaxy can piece together the universe's history, can trace its expansion, can predict its fate. We're made of atoms forged in stellar furnaces, arranged in patterns that can contemplate the stars themselves, can wonder about our origins and our place in the cosmic story. The universe doesn't owe us understanding. It doesn't care whether we figure out its secrets or not. But it also doesn't hide them. It leaves clues everywhere, patterns in ancient light, echoes of primordial sound waves, the slow dance of galaxies across billions of years. All we have to do is look carefully enough, think clearly enough, be humble enough to accept what the evidence shows, even when it contradicts our intuitions. As you drift off tonight, maybe you'll carry some of these ideas with you. The thought that space itself is expanding, that most of what exists is invisible to us, that the light falling on your pillow has been travelling through the cosmos longer than stars have been burning, The universe is patient with its mysteries, revealing them slowly to those who ask questions and search for answers. Sleep well, and may your dreams be as vast and wonderful as the cosmos itself. Thank you for journeying through the universe with me tonight.